My name's Adam Mars. I'm a senior graphics engineer at Nvidia. And today I have the privilege to talk to you about one of my favorite subjects, which is real-time ray tracing in games. And a lot like Eric Haynes, who gives great talks, I have stolen from him the great idea of using a motivational quote to start off the talk. The quote on the screen here is from Turner Whitted, who many of you probably already know who Turner is, but he is a pioneer in our field of computer graphics. In this quote, Turner is recalling a conversation that he had with an executive when he was working at Bell Labs, and the executive asked him what it would take to ray trace in real time. And so Turner told him, or was recalling, I proposed a vast array of Cray supercomputers, one per pixel with a red, green, and blue light bulb on top of each one. It was meant as a joke, but it turned out not to be. At the link below, you can see a more full telling of that story from Turner himself, and learn more about the history behind global illumination and computer graphics and ray tracing. But if we fast forward a bit and focus in on more recent history, specifically for ray tracing, 2 years ago, Microsoft introduced the first hardware-independent GPU ray tracing API called DirectX Raytracing. And at SIGGRAPH that same year, we announced the Turing GPU architecture and our RTX series of GPUs. These GPUs provide hardware acceleration for the DirectX Raytracing API, and now additional APIs, including Falcon Resources. And this is really important because this was an inflection point in real-time graphics, making it possible for new games and new applications to ship with visual effects that weren't possible or practical previously. So as it turned out, oddly enough, Turner's joke of having a supercomputer behind every pixel kind of became a reality. Since I'm the first session speaker today, and everyone in the audience may or may not have had time to fully dive into ray tracing yet, I'm going to talk about the benefits of real-time ray tracing, what those benefits bring to games, just to make sure that we're all on the same page. You know, it's said a picture is worth 1,000 words, so I'm going to show you the benefits of ray tracing first, and I'm going to use Remedy's fantastic game control to do that. So here's a quick overview of the benefits I'm going to talk about. The first and probably most obvious benefit is image quality. It's probably the first thing you think about when you think of ray tracing. With ray tracing, like I said earlier, you can accomplish visual effects that weren't possible or practical previously when you just had rasterization. A popular example of this is reflections that include interreflections, which really aren't possible with rasterized cube maps. And now that ray tracing is part of your graphics toolbox, in addition to rasterization and other techniques, you have this new tool at your disposal. And ray tracing isn't meant to just replace everything, including rasterization. The two are kind of a dynamic duo. Each tool is sort of meant for different jobs, and together, a hybrid rendering system with rays and rasterization is super powerful, enabling great performance, flexibility, and visual fidelity in different scenarios. And finally, and maybe most importantly for games, the addition of real-time ray tracing really has the ability to revolutionize the production pipeline. Long pre-processing and baking steps can be drastically improved or even discarded entirely. And this can help increase artist iteration. So they're spending less time on tedious tasks or waiting for light bakes to complete so that they can iterate on look dev much faster, really unlock the creative freedom that they'd like to have and not be held back. And this new runtime capability of ray tracing allows us to revisit our assumptions that we've had for such a long time about what's static and what's dynamic in a game or during the production of a game, what's baked and what's not. So let's dive into an example of a game that attacked this and then came out with great results on the other side. So here's a shot from early on in Control. This is raster only. There's no ray tracing in this shot. This is using screen space reflections. Very common technique for reflections nowadays. It's pretty effective. At first glance, you'd say, hey, this image is pretty good, especially compared to images from a few years ago. But if you look closer and inspect the image more, you'll sort of find some things pop out. I don't know if you all can see my mouse, but I'm going to point to specific parts of the image with my mouse. The first one is the reflections that are, well, just behind the fire extinguisher. If you look at that, it's as though the fire extinguisher is being multiplied many times. And this, of course, isn't right. This isn't what you would see in real life. If you look in the upper right of the image, the light, the area light that goes across the left side of the image gets blurred out and then completely disappears, which is not quite correct either. The glass in front of the desk doesn't have reflections on it. So if we ray trace instead, we get a pretty different image. I'll flip back and forth between these two. And you can see now the area with the fire extinguisher now looks much more like what you would expect it to look like. Also, the alarm at the top above the fire extinguisher appears in the reflection as well. So substantial image improvement there. So why couldn't we do this before? Why was screen space reflections failing? This diagram more or less shows us why. When you want to compute reflections, you have a primary ray that goes from the camera or the eye to the surface that's being hit. And then you need to compute what that surface would reflect or what appears in the reflection from that glossy surface. In rasterization, you don't have the information about this surface necessarily unless it's also hit by another ray coming from the eye. So the ability to shoot a single ray from this point to whatever's reflected in an arbitrary direction is just not possible unless you had a cube map or some rasterized image-based solution for every point across everything that's visible, which is really just not practical. So ray tracing brings this new tool and new ability to have accurate, incoherent visibility. So what you're used to, rasterization, is a very coherent set of rays from a single view origin. And it's very fast. It's built this way to be accelerated by hardware. It's very effective what it does. But there are instances like in reflections where you need to be able to trace a ray from an arbitrary point in an arbitrary direction, and you may not need a bunch of the other directions near it. And this is exactly the case in reflections. Here's another example that's more difficult, where we have an image, with glass, and the glass is going to be very reflective. In this case, screen space reflections don't have any data on the screen for the things that are reflected in these mirrors or in these glass walls. And the glass is also transparent, which adds another layer of difficulty to the problem. If we swap to ray tracing, we can then shoot the rays that we need into the scene, into content that's not visible directly from the camera. And so we see our character and some stairs and the other parts of the environment that are able to be traced with ray tracing, but screen space methods just don't have the data to do this. So here's a diagram of this scenario too. Now we have a transparent layer, surface in between the eye and the opaque surface. And when we hit that surface, we can then trace a ray to what would have been reflected in that glossy surface. This is essentially our character and the stairs and the other parts of the off-scene geometry. So adds a large amount of visual information into the image that previously was not there. Okay, so it's not all about reflections. Reflections are very shiny and fun to show, and they really catch your eyes. But there are other really important elements, visual elements of an image that ray tracing can improve substantially. For a very long time, we've been using shadow maps to compute shadows and occlusion in a scene. And this has very well-known limitations that have plagued games for a really long time. Here's a shot from Control in a room with a bunch of chairs. And if you notice, if you look at this first chair in the foreground, you'll notice that there aren't really any shadows underneath the front two legs of the chair. Same thing with some of the chairs behind it, and the cabinets on the back wall, they look a little bit stark as well, not a whole lot of shadowing. Typical kind of stuff you would see with shadow maps, where they're either shadow resolution of the shadow map makes it so there are no shadows in your final image, or the shadows appear detached, or called Peter panning, where an object appears to float in the air because the shadow is not actually attached to where the receiver and the occluder touch. This is ray traced contact shadows. So this is a hybrid technique that Remedy has done where they actually use shadow maps and ray tracing together. So an example of that hybrid technique. So they can use the ray trace or the shadow maps for performance for a lot of the scene, but use the ray tracing just for those contact points so that they can get very sharp, accurate contact shadows. So now you see there are nice shadows underneath our chairs. And if you look in the back of the room, the areas where there are shadows close to the bookshelf walls, you get correct occlusion. All right, so hopefully these examples convince you like, oh, cool, this is something I have to have. I really want this in my game. The visual improvement is excellent, but I don't know where to start. I don't like, what do I do next? Fortunately, in 2020, unlike in 2018, there's tons of educational material out there and a lot of really good educational material. So the first place you should stop to learn about ray tracing is Eric Haines' Raytracing Essential series on YouTube. It's a 7-part video series. If you're unfamiliar with ray tracing completely, this will get you through all of the beginning parts and the basics, and even some advanced stuff to get you the background knowledge algorithmically that you would need to then move forward. So after watching those, your next stop would be a modern graphics API that supports ray tracing. And the sort of big two at the moment would be Microsoft's DXR, or DirectX ray tracing, that is part of DirectX 12, and Vulkan ray tracing, where ray tracing is supported through extensions. Nvidia is deeply engaged with Vulkan in addition to DirectX ray tracing, and we shipped Vulkan 1.0, 1.1, 1.2 specs on the day they were released, and we're increasing Vulkan support in our development tools like Insight Graphics. We're chairing multiple Vulkan initiatives at Kronos, and Neil's going to talk a lot more about this later. And additionally, we contributed VK-Ray to catalyze and get Vulkan ray tracing started and off the ground. Okay, so for me at least, a lot of the time, getting started is the hard part. And I can watch all the talks and videos and read papers, and it's all good. But to really get going, I just need to look at code, and I need to compile it, run it, and then play with it. So I created a very, very small DirectX ray tracing code sample to get you started with the basics. So you can get past that, the early stuff where you're just learning the beginnings. It's on GitHub. It's free. Um, you can pull it down, compile it, and run it very quickly and easy. And if you have any problems, just send me a message or post something in GitHub issues. As you work through that code sample, you'll realize in DXR, the high-level ray tracing process is essentially this. Vulkan ray tracing has a very similar process with some different names, but more or less the same process, where you start from building acceleration structures over your geometry. This would be a BVH, bounding volume hierarchy. You build that acceleration structure over your geometry. Then you want to load and compile your ray tracing shaders. So DirectX ray tracing and Vulkan ray tracing both have new shader types. So in addition to your vertex and pixel shaders, you're going to have a ray generation shader, a miss shader, and then hit shaders. So when your rays are cast and they hit something, you can run code that you've written to tell it what to do next. So you'll load and compile those. Then you'll create a ray tracing pipeline state object. This is very similar to the pipeline state objects you're already used to with your existing vertex and pixel shaders, but it's specific to ray tracing. Then you'll allocate and populate a shader table. This is the part that's quite a bit different than the other bits that you're used to. But this is just a flat piece of memory that you put your ray tracing shader and root parameters and constants and values that you'll use in those shaders that you'll need for all the different materials and geometry that you're going to ray trace. So importantly, remember that ray tracing is a more global than rasterization, in that you could hit any material, any surface, any piece of geometry at any time. Whereas with rasterization, it's very view dependent. You can set it up and optimize it to be that way. So this shader table is sort of the bind between your geometry and your materials and the ability to evaluate any of them at any time. And then finally, you'll call a dispatch, sort of inspired by compute shaders, but it's dispatch rays. This will launch your ray generation shaders and allow you to start the ray tracing process on the GPU. Okay, so you've got a sample, you've got a basic idea of how things work. Here's all the rest of all the tutorials and things that I would recommend. For DXR, there was a great course at SIGGRAPH in 2018. The entire course is available for free on YouTube. And Chris Wyman has a companion website where you can see PDFs and stuff if you want to go through it slowly and absorb all of the details. Microsoft has posted excellent functional specification documentation for DXR. They've also posted ray tracing samples and tutorials. So if you've gotten through my sample or you don't want to use mine, that's totally cool. Microsoft has samples and tutorials to show you how to do ray tracing with DXR and DX12. And then Nvidia, we have posted several ray tracing tutorials as well to walk you through the process. They're available on GitHub. And there are also 2 pages here, the tutorial part 1 and 2, that walk you through and tell you what every step is doing. Finally, or not finally, but there's also a lot of Vulkan ray tracing resources as well. Kronos has an overview of how it has been, how support has been brought to Vulkan. You can see the extension specifications at these links. And we also have similar ray tracing tutorials for Vulkan available on GitHub and a companion page that will walk you through what each step does and what it's for, just like with DXR. Finally, you also have tools. So you've got code, you've got tutorials, and now there are tools that will help you debug as you run your application, as you walk through the frame to figure out what's going on, maybe what's wrong. Insight Systems is more of a system-wide view of your application behavior across CPU and GPU. There's just a boatload of functionality in here that's really great. You can do multi-GPU graphics traces, GPU workload trace, CPU performance counter sampling. This works on Windows and Linux. Insight Graphics is great as a debugging tool for the GPU. And it has, one of the features I love about it is it has an acceleration structure viewer. So once you build that ray tracing acceleration structure, you can go in, hit capture, and then look at the actual BVH that's in memory and fly around in it. So if there's some corruption in memory in your geometry or some problem in the ray tracing that you're noticing, the first thing you can do is go in and make sure, am I actually ray tracing the right thing? Finally, there's Insight Aftermath. This is the ability to capture what went wrong after a crash happened. So it'll give you crash dump files for Windows 10 and Linux, and you can add markers to correlate the location of a crash with the crash itself, and help you figure out what's going wrong after the fact. The shader profiler for D312 and DXR will be out in the next release, which is really exciting. You'll be able to actually profile and see performance directly in the tool. And Insight Aftermath for Linux will be coming out soon as well. One more resource, you may have heard of this book already, but we released this book in 2018, and it's available for free for everyone. Just go to this link, the Springer link. You can download Ray Tracing Gems for free. There's a content overview, a video here that Eric Haynes has done that will walk you through every chapter of the book to kind of give you an overview of what the book's about. And if you're old school like me and like to have the physical book in your hands while you read through it, you can buy it on Amazon using print on demand. And it goes through everything that you're going to want to know at the beginning as you get started with ray tracing. A lot of the questions and ideas that you may have in the beginning, they're covered really well here, including ray tracing basics, intersections and efficiency, reflections, refractions, shadows, sampling, denoising and filtering. There's a chapter in there on how UE4 does denoising and filtering for cinematic rendering, hybrid approaches and systems, and GI. So I highly recommend you check out the book as well, in addition to the other learning resources you have. And I think that's about my 30 minutes. So if you have any questions, you can ask them now, or you can send me a message on Twitter. My direct messages are open.